In this video, I will explain all the necessary parameters for two temperature model fit, the prerequisites, starting from the parameters that should be typed in the program. For fitting, you need to put the pulse parameters. So here you put wavelengths and pulse full width at half maxima in picoseconds. In our case, it will be 0.035 femtoseconds at 100 nanometers. Additionally, you can include fluence here. However, this fluence is not used for the regular fitting. This fluence used only for depth-dependent to temperature modeling without fitting. The fluence that will be included for fitting, it's either for fluence that you include here, for example, here at 5, or another option is when you have fluence dependent measurements, fluence is included from the header of the file. So the pulse parameters, you include wavelengths, you include full width half maxima. Then you include sample parameters. You include extinction coefficient, which is imaginary part of the optical constant K. Then you have sample thickness, the thickness of your sample here. In our case, for example, it will be 80, and for the second number, you should not change. It does not matter. It's also for depth-dependent simulation. How many layers do you have? For depth-dependent, additionally, you sometimes want to increase a little bit the thickness, because the last layer, it will be not the layer number 80, it will be layer 80 nanometers, it will be 78, so that's why it was 82 here, but you need the 80, and then this number you can leave unchanged, you can put anything one. The only parameters for fitting important is this one, the sample thickness. Then you need reflectance. Reflectance you can measure from the experiment, how much you have reflectance on your 800 nanometers to know which percentage of the palm pulse was reflected, and which percentage will be absorbed is based on the sample thickness and its extinction coefficient. The next parameters, so here we skip this section, the debye temperature, the thermal conductivity and escape time. Those, the debye temperature is for the previous models. Use another option to get the lattice heat capacity. The standard procedure used heat capacity from the file and from the polynomial. That the program will use a polynomial fit of the experimental data to give you heat capacity, and then it will be constant outside of the range. So this is in more details later when I will show you the heat capacity file. So you ignore this debye. The thermal conductivity and escape time also used only for depth-dependent model, and I will go into detail in the depth-dependent video. Then you have density and molar weight that you should include from the previous references. That these parameters will be used to recalculate the heat capacity in the correct units. The previous publication usually used millijoule divided by mole divided by Kelvin, but in these models we are interested in units of density in kilograms per meter square, for example, in volume. Then or in meter square, we need to change this heat capacity in converting another units. That's why you need to provide density and molar weight. And the gamma, this is the coefficient of electron heat capacity. We use linear model where the electron heat capacity equals gamma multiplied by the electron, and this parameter is also you should get from the previous model. the next two parameters are fit parameters if you do manual fit. So you don't have to know it beforehand. You can fit it here as a manually, or you will set up advanced fit. Then you have initial temperature, which is also needed only for depth-dependent model. For you either use here the fluence dependent for fitting the temperature you define here, or if it's temperature dependent, the temperature will be in the header. And lastly, two parameters, Grunayson parameters, those are needed for electron and lattice stress. So firstly the electron parameter, secondly is lattice, to then get the photo-induced stress. So those are parameters that you should have to include first as a prerequisite. You have to know the gamma, you have to know the density, the molar weight, and you have to know the reflectance, sepal thickness, excision coefficient, and the laser parameters, pulse, width half maxima, and the wavelengths, central wavelengths. Besides that, you should have the heat capacities file. So, for example, I have my heat capacities files here. I will show you what it consists of. If I go to my heat capacity, my heat capacity consists of only two columns, no labels, and this is the digitalized heat capacity. From 0 to 300 kelvins in the correct units. Make sure that you should here have millijoules, not joules, millijoules per mole per kelvins, and here also gamma in millijoules. And let's see, I need to provide the file direction for my heat capacity. So for this region, I will use the browse function. However, if I include heat capacity like this, the browse put heat capacity here, I need to copy paste inside of this window, I include heat capacity. I also will fit only within some region for lattice from 5 Kelvin, let's say, to 290, and then it will be constant outside. You can see that, for example, here I have initially I have very slow variation, and after some temperature I also have very slow variation. So I assume constant is already at higher temperature. I can assume that my heat capacity already a constant. And then of course I need the file for example, here I have power dependent measurement set, and then it will be fluence dependent. For two temperature model, you cannot use power in milliwatts, it has to be fluence. For example, my file here already prepared from the pneumaticity program. This was channel 1. From the pneumaticity program, as you can see, I have my fluence in the header. I have already my delta R by R files. For example, I will open the first one, the last one. You can see that it's already renormalized, so it's 0 and relative change. It can be, it does not have to be divided by R, but it's better to be divided by R. The thermoreflectance coefficients will fit the two temperature model to the thermal reflectivity signal, but more in detail about this in the next videos. Here I just show that I can open the same files. You can see that this is the first file. I open it here, and then I can go to the last file, and then the last file is already opened. One thing to note that here I open less points. It's due to the computational load. Is a good idea not to open all points, because firstly it will take much more time to open all files. For example, here if I open all files, additionally I have some this program actually let's open all files. So I need to put, not ignore less points. I need to open all points, and as you can see, 40,000. It will take much more time for program to run the algorithm for that region. I usually choose something like 1,000 points in the fit region, and as you can see, it does not just throw points out, it averages over those points that it does not use. So that's it. Quick recap: you have to fill these parameters, not all of them, but just pulse parameters, wavelengths, full width, half maxima, sample parameters, thickness, reflectance, extinction coefficients, and then material properties, density, molar weight, gamma, electron heat capacity coefficient, and file for lattice heat capacity. Note that sometimes it can let you open the file even if it does not find the file. Let me change to, for example, disk G. So I still can load and no issues, but then your model will not work. So check that the heat capacity is correct, and then of course you need the file based on the nematicity program or text shuffle. You need already file in that format.